Hello everyone. We are now going to start our units on trig. So this is our first of many and our first of chapter 6. So a lot of this will sound familiar from last year when you started trig a little bit in Math 3, but there's also some new things as well. All right, so section 6.1, we are going to focus a lot on definitions and things like that, and we're going to be talking about angles and their measures. Something new, we are going to be converting between decimal and degree, minute, and seconds, which we'll talk more about in just a second. We'll be finding the length of an arc, which you did in Math 3, but we'll talk about that again. You also converted from degrees to radians and radians to degrees. And you found the area of a sector. So those are all kind of review topics. And then also new to pre-cal is finding linear speed and also angular speed, which we will talk about as well. So just kind of a refresher here for what we talk about when we talk about angles. We know that an angle, of course, is formed with two rays. We talk about the initial side of the angle here and the terminal side, of course, being the other side, the ending side. We call, of course, this the vertex. And we can talk about an angle going up like this and this counterclockwise rotation. We call that a positive angle. This will become, of course, the x-axis in just a minute. But we're just kind of freehanding it here. But the x-axis here, and then we open up in this counterclockwise way for a positive angle. If we open in a clockwise direction, so you can see if the angle we're talking about is in fact started here and going the other way, we would call this a negative angle. So that's how we define a negative angle, is going clockwise, a clockwise rotation. And then, of course, what is important to remember is that I can go around a circle as many times as I want to in either direction. So you notice this angle right here looks a lot like this first angle, but it was actually formed by going all the way around the circle and then going a little bit more. So we could do that over and over and over again, and we can have, obviously our angles aren't going to look that different, but they would have a larger, more positive measure if I go around the circle more than once. Okay. So an angle theta is said to be in standard position if its vertex is on the origin, and you've seen this before. And again, you can see these pictures here of a positive angle. The initial side is the positive x-axis, and we are going in this counterclockwise direction to give us a positive angle in standard position. And then over here, you've got the example of a negative angle. Still, the initial side is the positive x-axis, but we are going in this clockwise direction to form a negative angle. All right. When an angle is in standard position, either the terminal side will lie in a quadrant or it will lie on an axis, in which case we call it a quadrantal angle. So again, these are just some examples for you to look at here. I would say that this angle in this example here lies in quadrant 2 because the terminal side of the angle, as you can see, opens up and lies in quadrant 2. This angle here, I would say, lies in quadrant 4. You can see the terminal side here lying in quadrant 4. And then, of course, if I have an angle like this, again, starting here, going all the way around, landing on the y-axis here, I think you could probably tell me what the measure of that angle is because you understand 90, 180, 270, 360. You understand all of those things. But this, again, would not lie in a quadrant since it lies on the axis between two quadrants. So let's practice that for a second. You might want to pause and practice this, drawing each angle in the correct position. You don't have to be super specific here. Just make sure you get that terminal side in the correct quadrant. So if you've paused, you might want to now check into this. 135 degrees. We know we're starting here with our initial side. I know that that's 90 degrees if I open up here. I know it's 180 if I open up all the way over here. So 135 is going to be somewhere in this second quadrant. So this would be about a 135 degree angle. Negative 180. Negative 180, of course, I'm starting here. Negative going this direction, so negative 180 is actually going to be right on this line here. Notice that a negative 180 degree angle and a positive 180 degree angle are actually land in the same place, have that terminal side on the x-axis over there. 90 degrees, of course, we know that lands right up here. So this, of course, we know to be a 90 degree angle. And then 495, of course, is greater than 360, but just consider the fact again that I can go around this thing as many times as I want. So if I start here and I go all the way around, by the time I reach here, that's 360. I actually have 135 more to go. So I'm actually going to end up back in the second quadrant, and you should notice a similarity between that first problem and this last problem, because they actually are landing in the same spot. They have the same terminal side there. It's what's known as coterminal angles. But notice that, again, I could go around 360 again. I could add 360 again and come back to that same spot. All right. So like I said, something new, something that's not terribly used, it's not used a lot, but sometimes when we have a fraction of a degree, and you've seen it before, like 35.24 degrees or something like that, we could also write that fractional degree in what we call minutes and seconds. So it's really just more of a conversion that you'll have to learn and practice. This is used a lot with latitude and longitude. I think like the military uses it a lot to be exact in their where they need to be or where they need to do things or whatever. So this is really just for you, again, kind of a conversion. So we define 1 minute, and we use this to mean 1 minute. 1 minute is known as 1/60th of a degree. Okay, so that means 1 second, of course, we already know to be 1/60th of a minute, and that would make it 1/3600th of a degree. Okay, so again, let's think about that, think about what that means. So as an example, an angle of measure 30 degrees, 40 minutes, 10 seconds is written like this, and this is how it's read: 30 degrees, 40 minutes, 10 seconds. All right, another way to think about this conversion here, if 1 minute is 1/60th of a degree, perhaps it would be easier for you to think about it as 1 degree is 60 minutes. Maybe that would help. 1 minute, of course, is 60 seconds. This is something that you already kind of know in order to do that. So really, as far as we're going to go with this is to convert. We're going to practice converting between what we know to be decimals and what we've now learned to be minutes and seconds. If you're given a problem, sometimes you might be given a problem in minutes and seconds, and if you're not very familiar with that, you might want to think about what that means or even convert it to a decimal. But really, this is all about just the exposure and just a few examples, just so if you ever see it, you're not like, what on earth is that? Why is it written like that? All right, so we are going to start by converting something given to us in degrees, minutes, and seconds into a decimal. All right, so again, this is really just more of a conversion thing for you. The 65 degrees is going to stay the 65 degrees. I'm not concerned about that. So I still have my 65 degrees. And what I'm adding to that, you could think, is this 9 minutes. Well, what is that? Well, I could, again, using my conversion that we just talked about, I could just treat that as 9/60. Why would I do that? What does that even mean? Well, what I'm trying to say here is that this, again, from using my conversion, 9 minutes would be 9/60ths of a degree. Right, I'm just using that conversion from before. And then, of course, the 17 seconds, also using that conversion, would be 17 3,600ths of a degree. And so I could convert these fractions to decimals and just kind of sum this all up. And if I did that, I mean, you could even use your calculator here to convert these to decimals, I'd get about 65.1547 degrees. And so that, you know, these are equal. This is, you know, that's more exact. That's nice. They have their reasons for being used. So that's how you would convert it in that direction. All right, let's think about converting it the other way. If I'm given the degree and I want to convert it to the minute and second notation, how would I do that? Well, again, I've got my whole number here of degrees, so I'm just going to leave that over here to the side. I already know that that's going to be part of that. Really, I'm just concerned about the fractional part, this 0.497, or 479. All right, so let's think about what that means for us. I think the easiest way to do that is to first write it as a fraction. So 0.479 is 479 over 1,000. And this, of course, is in degrees. So if I want to convert it over, I can just use my conversion and say that 1 degree, you know, degree on the top and degree on the bottom is equal to 60 minutes. Here, I could do that. In which case, I would, if I just multiplied that out there, notice the degrees would cancel, I'd be left with minutes, and I'd actually be left with 2,874 over 100 minutes. Okay, so what is that? Well, that's the same thing as 28.74 minutes, right? If I just divide that out, I get 28.74. Well, now I've kind of taken care of some of my fraction, and I have a whole number of minutes here, so I'm going to go ahead and write that up here. I now have 28 whole minutes, I know that. I still have a fraction that I need to take care of. This 0.74 is still there, so I'm just going to carry on and take care of this decimal and try to convert it to seconds. So at this point I have 0.74 minutes, and to use yet another conversion here, I'm going to say that 1 minute is 60 seconds. My minutes are going to cancel, and I'm going to take this down to seconds. And if I multiply that out, I get 44.4 seconds. So that's about as far as I can go. So I'm going to just take that down to 44.4 seconds. I don't love that there's still a decimal here, but I think that this is good enough for what we are trying to accomplish. So don't stress about this particular topic. It's really just some conversions, and you know, you've done that quite a bit in the past, and you'll have a chance to practice that as well. Okay, radians. This is something that you kind of defined last year. I'm gonna also post a video of an activity. It's kind of like an activity that you did last year, but it was near the end of the year, defining what a radian is. So let's remind ourselves of what that is, and if you need to check that video out for a little bit more clarification, please do so, because this topic is not going anywhere. All right, so a central angle is a positive angle whose vertex is at the center of a circle. The rays of the central angle subtend or intersect an arc of the circle, so you can see the arc here. If the radius of the circle r and the length of the arc is the same as r, so if this radius is r and I kind of take that radius and, you know, bend it over so that it like is exactly on this arc here, I haven't changed it. This is r, this distance is also r. Then the angle that is formed here is defined as a single radian. That's how we defined radians. So we didn't have to talk about angles in degrees all the time. We could also talk about them as radians. And in fact, we do a lot more calculations with radians. So when we talk about an arc length, we had a way that we would talk about the length of an arc of a circle. You know, if you had an example here and you knew that the radius was, let's say, 4, and you had an angle theta, and you wanted to find the actual arc length here, what we did a lot last year is we said we treated this arc as a fraction of our entire circle. So we said we have, let's say theta is 30 degrees. So we would say I have 30 out of the entire 360 degrees. That's the fraction that I have here. So this is the fraction of the circle I have. And if I had the whole circle, then the arc length would be, we know circumference to be 2 pi r. The arc length, the whole circle's circumference would be 2 pi times the radius 4. So that would be 2 times pi times 4, which is 8 pi. And so what we ended up doing was multiplying that out. We said, what fraction do we have times the entire circumference? And that's how we got the arc length. Essentially, what we were doing is this right here. If S is known as the arc length, we were simply multiplying that theta, that angle, in radians. It has to be in radians. And we were multiplying it by the radius. And so that is what we were doing. We were essentially converting our degrees to radians and using this. So you could go straight to using this now. Notice a couple of things you should see here. If S is the arc length, R is the radius, and theta is the angle in radians, if the radius of the circle is 1, then that leads us to simply S equals theta. And this we talked about a lot when we first discovered the unit circle last year. In the unit circle, when the radius is equal to 1, the arc length and the central angle have the same measure in radians. And so think about that. If we make our circle bigger, if we change the radius from 1 to 2, for instance, then our circle is going to get larger, and that would of course mean that this arc length would get larger as well. And so we would be multiplying here by that new radius, and that would make that arc length grow, as you would imagine the circle's growing. So that is that. Think about that for a few minutes. Remember how we did this, talking about the fraction of the circle times the circumference and how that relates to this arc length formula that we can now use. And here's a quick example. Find the length of the arc of a circle of radius 4 subtended by a central angle of 0.75 radian. Again, we're very fortunate that this is given to us already in radians. You cannot use this formula with a degree. So if I'm going to use S equals R theta here, this has to be in radians. So it's actually a very quick problem. The arc length would just equal 4 times 0.75. which of course is 3. And that would be the length here. This length would be measured in radians. Oh, actually, no. The length would be measured in meters because the radius was measured in meters. Okay, so there you have that. Very, very nice, easy formula to use. All right. Speaking of that, this should be something that seems very familiar to you. We understand that one revolution around a circle we know to be 360 degrees. We also know that to be 2 pi radians. So we understand 360 degrees and 2 pi radians are the same thing. So then, of course, halfway around a circle, 180 degrees is, of course, equal to pi radians. And we use that in our conversions. This, again, is something that you did last year, converting between degrees and radians using this. So let's practice that. I think this will probably be quite familiar to you. If I want to convert 210 degrees to radians, I say that I have 210 degrees. I'm multiplying again. I'm trying to cancel out here. I know that pi radians and 180 degrees is the same thing. So I multiply by essentially 1 here. My degrees cancel and I'm just left with radians. And if I multiply that out, 210 pi over 180, I of course can simplify that to 7 pi over 6. So 7 pi over 6 and 210 degrees are the same thing. You should be able to think in both. You should be able to think in degrees around a circle. You should be able to think in radians around a circle. And we are going to review our unit circle, which of course is very, very helpful. Okay, then of course negative 60 degrees, do the same thing, times pi over 180. This of course is negative. You can picture where that would be. Negative 60 degrees would be down here. Multiply that out and simplify, and of course I get negative pi over 3. So negative pi over 3 is again one of our unit circle values. You should think about that a little bit, where that would be, what that's all about. Of course, is in the fourth quadrant. More practice to come with that for sure. All right, so this next thing your book put in here. Oh, did I forget to? I did. Hang on. Before we do that, let's convert the other way to make sure we can do that. Pi over 4 radians to degrees. So if I have pi over 4 radians to degrees, I'm just going to do the flip of that. I'm going to put pi on the bottom and put 180 degrees on the top. Of course, I'm trying to cancel out my radians to get degrees, so the pi's cancel. And I have 180 over 4, which is 45 degrees. And again, that should be very familiar to you. Pi over 4 and 45 degrees. Should be able to think about that's right halfway through the first quadrant here. It should be starting to sound familiar to you. All right, you might want to pause and try these before, just to make sure that you can do that. So if I have negative pi over 3 times, again, 180 over pi, pi's are going to cancel. Negative 180 over 3 is negative 60 degrees. And then, of course, 2.5 radians. It says radians. These are in radians. No, there's no pi next to it. There doesn't have to always be a pi next to it. So please don't think that somebody just forgot to type the pi in or whatever. I could think of pi as 3.14. That's just a number there. It doesn't necessarily have to have a pi stuck right next to it. So 2.5 radians, I'm going to treat the same way. 2.5 times, again, 180 over pi to cancel out those radians and leave me with degrees. It's not going to be as satisfying because I can't cancel the pi's out, but I could simply multiply 2.5 times 180 and divide by pi, and I could still get, even though it's going to be something I need to round here, I could still get a degree measure for that. All right. Now, moving on to this. Your book, your pre-calculus book, has us doing here this area of a sector in this way, which is fine. If you want to read about that in your book, go for it. I'm thinking that you probably don't want to learn a different way of doing something if you're already pretty good at the other way. So when we talked in Math 3 about the area of a sector, we did it very similarly to when we talked about the arc length of a sector that we just reviewed. We simply said, again, we have this little sector here, and we want to know the area of it, and we treated it a lot like a fraction of a circle. So, as I said before, if I know that this is the radius r, and I know that this is the central angle theta, then all I really had to do was say I have theta out of 360 degrees, and if I had the entire circle, the area of a circle is pi r squared. So I simply have here the whole area of the circle multiplied by the fraction of the circle that I have. And if I was to work this out, I would get the same thing that they have here. I mean, it would be the same thing. If I change this pi here to 180 degrees, because I know that that's what that is, notice I have 180 over 360, which of course is the 1/2, and then the pi I have here, and then the r squared. So I mean, that's where it comes from. But I don't know that you need to necessarily think of it this way. I think it's much easier to think of it as, here's the whole area of the circle, here's the fraction of the circle that I have. And so now I can find the area of that sector. So, I mean, again, either way you want to do it, Let's do an example. Find the area of the sector of a circle that has a radius of 3 formed by an angle of 45 degrees. Round your answer to 2 decimal places, okay? So if I had the entire circle, again, the area of the entire circle here would be pi times radius squared, which is 9, so it'd be 9 pi. I don't have the whole circle though, I have a fraction of it. What fraction do I have? I have 45 out of 360 degrees. And so I could say, multiply that by 9 pi. And I could work that out. Alternatively, what I could also say is that I have 45 degrees, we know to be pi over 4, right? That's the same thing. 45 degrees is the same thing as pi over 4 radians. I could treat it like that. I could say that I have pi over 4 out of 2 pi. That's the fraction that I have here. Pi over 4 out of the entire 2 pi. What would that be? Well, that would be pi over 4 times 1 over 2 pi. Cancel those pi's out. That's an eighth. Well, that should sound familiar. An eighth. Isn't 45 degrees an eighth of an entire circle? So wouldn't this be an eighth if I was to simplify that? So lots of ways you could do this. You essentially have an eighth, any way you slice it, an eighth of 9 pi. So that is 9 pi over 8, or again, I could convert that into a decimal. Let's see what that would be. 9 pi over 8 would be, I would just leave it alone. Let's just leave it like that. It'd be easier for everybody to think about.